And Matt Heydeman is here to tell us about your BPS black holes.
Okay. Hello, everyone. So my name is Matt Heydeman. I'm from IIS and joint with Princeton. And I'm going to be talking to you today about near BPS black hole microstates from supergravity. And I'll say what I mean by microstates. I'll say what I mean by near BPS. I'll even say what I mean by black hole. I think supergravity everyone should know in this audience. So that's the one I want to explain. This will be based on 2 papers and several more related things to appear in the future, as well as several more background references with my collaborators, Luca, Joaquin, Wenli, and Jan. So let's begin with the very broad overview. So what is a basic challenge of quantum gravity, or what are some basic challenges? Well, we could try to tackle the unitary collapse and evaporation of a Schwarzschild black hole in 4-dimensional asymptotically Minkowski space. I won't be so ambitious and won't attempt this, so we won't try that. We could try something maybe a little bit less ambitious, is to at least compute the exact density of states of a Schwarzschild black hole in 4-dimensional asymptotically, or in perhaps a stringy completion. And we would expect something, so something where we could have individually spaced microstates as a function of energy, and perhaps if we had sufficient power in theory, we could compute this kind of thing exactly. In maybe some very specific examples, we could compute this, but we want to learn some more general lesson about gravity. And so I'm going to say that we won't even attempt that. What I will try to attempt in this talk is to compute what I would call some semi-universal features of the density of states. So a quantum density of states and not a classical formula. And then we're going to compare the features of density of states that we find with things we expect from supersymmetry, ADS-CFT, and string theory. So in particular, I'm going to discuss supersymmetric gravity theories describing black holes in what I call the near extremal or near BPS limit. And this is a limit in which we're going to be able to make some exact statements about what I will call the Euclidean gravitational path integral, or the path integral for short. So let's talk a little bit about that. I guess the key idea that I'm going to say that comes out of this work, or the key output, which is perhaps a little bit of a surprise, is that we have some signature of microstates from a path integral perspective. So I'm talking about computing something like Z of beta, and computing Z of beta for near BPS black holes. The supersymmetry is important. We can get a signature of microstates. We can get a signature of the supersymmetric index, and other things that have been predicted from string theory and ADS-CFT. So this is the question. I'm already telling you that the answer is affirmative, and I'll explain exactly how this arises and in what systems we can do this computation. So the Euclidean gravitational path integral. Depending on who's seeing this talk, this question mark may or may not be here. For this audience, the question is there because, as we all know, there's this famous statement that you could say, assigned to a Schwarzschild black hole, that the entropy is proportional to the area. It contains h bars, so it's clearly counting something quantum. But at this level, this is just a prescription to declare that a black hole has this entropy, or compute a semi-classical temperature and say that it corresponds to this entropy. We can do a little bit better if we do something like the Gibbons-Hawking prescription, where we have in mind a path integral approach where we fix some boundary conditions on the geometry and declare that I'm going to somehow integrate over all manifolds that satisfy the boundary conditions, weight them by their classical action, or integrate over all metrics that satisfy the boundary conditions, compute Z of beta, and then use this to extract thermodynamic quantities. Now, we don't know exactly how to do the sum over metrics. We know that these kinds of functional integrals can be usually approximated by saddle point. So you might want to say that Z of beta is given by a sum over saddles of some, the exponential of the classical action weighted by the one loop determinant. This is an approximation. We don't really know which saddles, though, compute in a general setup. We don't know how to compute the one loop determinants in the most general case. We don't know if this is convergent. I mean, this whole expression might be meaningless. However, what I'm going to say is that maybe when Gibbons and Hawking were first thinking about this was a good idea that seemed to get some of the right answers. But we've come a long way since then. And we know now that string theory and ADS-CFT provide an actual UV completion where you can, using independent arguments, check some of these formulas and check that this Euclidean path integral, which by some definitions has no reason to work and has no reason to exist. We have an independent check of this. And certain quantities are protected. So you can in a field theory and reproduce it from a gravity calculation. And that's very impressive, and we should understand why, and we should try to understand how far we can push this. And in particular, we might want to ask, is this sum over saddles related to a sum over microstates in some Lorentzian setup, or is this just some mathematical gadget which by some accident can count what the real black holes or whatever replaces black holes when we take all the stringy correction into account? It's unclear, but my goal will be to show you that we get good mileage out of this in a broad range of examples. So I can quickly review extremal black holes in higher dimensions. I think almost every talk has had something to say about this, so I won't spend too much time here. Now I'm drawing this funnel shape that we've seen before. Oh, well, if I could control the mouse, maybe like this. So I'm drawing this funnel shape that we've seen before. I've been a little agnostic about what we put down here, but I want to emphasize that I'm really going to be in periodic Euclidean time all the time. So the angular direction, tau, this will be a circle at asymptotic infinity. It'll also be a circle of length beta. Beta will be the inverse temperature. And these black holes will be ADSP, thermal ADSP across SQ, or something that has asymptotes to ADSP. And then there'll usually also be some squash spherical horizon. In the example I'll focus on today, we'll have something like ADS5 cross S5, or a black hole with ADS2 cross S3 cross S5, something like that. And the reason why I'm considering an extremal black hole that has this ADS2 throat in the end will be that the idea, roughly speaking, is that when we turn on charges and rotations, we can have a macroscopic black hole where the temperature goes to 0, but the black hole remains macroscopic. And there's something a little funny about this extremal limit, which was covered in Dieter's talk already, that this ADS2 limit seems to sit at infinite distance and so on. But I'll point out some perhaps even more pathological features of this, which is that if we the energy and the entropy computed from hole and expand around the low temperature, we'll have some extremal values, E naught and S naught. These are the values you would get for the exact ADS2 geometry. Again, in a semi-classical picture, plug the black hole into the action and compute thermodynamic quantities. And when expanding at low temperature, we'll find that these quantities scale like T squared and T respectively, with some energy scale I'll call the gap scale. Now, the funny thing about this formula in particular could be something like the energy. Now, again, as we saw in the previous talk, the energy of a single Hawking quanta goes like linear in T. Whereas the energy of a black hole, as I expand at low T, that's quadratic in the temperature. And what's funny is that, of course, usually the T squared will win, but at low enough temperatures, the linear in T wins. And when the energy of a single Hawking quanta is of the same order of magnitude as the energy of the black hole, or the difference in energy because of extremality, you can no longer say that the thermodynamic equilibrium holds. So in some Hawking's calculations simply fail for sufficiently low temperatures. This was pointed out in this paper by Pascal, Schwartz, Shapir, Trivedi, and Wilczek, and several other authors in follow-up papers. So this is a problem with semi-classical black hole thermodynamics. And we might say, well, the problem is that you tried to use a classical formula in a limit when the classical formula failed. In other examples in statistical mechanics where that happens, we say that you're not supposed to use classical statistical mechanics, you're supposed to use quantum statistical mechanics. So my claim will be that we can fix this problem by properly doing quantum mechanics in the throat region, which is exactly in this geometry that dominates at low temperatures. And that will be a key point of this. There's another problem with this ADS2 region, which is that it's often said that ADS2 holography has to be trivial. That if you turn on finite energy excitations just in the gravity limit, back reaction will destroy the gravitational, will destroy the boundary conditions and mess up your ADS2. So we might ask if you can put other things here, but working just in supergravity, solving some Einstein supergravity, you might conclude that a dual conformal, one-dimensional conformal field theory would either be topological or would have ground states too. Yeah, global ADS. Yeah. It could be dual. I'm in Euclidean, so I'm literally thinking about a disk with a thing, but you could talk about two asymptotic boundaries. That's correct. I think maybe in this paper they were talking about Euclidean in the fragmentation paper, but yeah, you can talk about the two boundary case as well. So I mean, this is a problem that we might be fine with. We can talk about some superconformal, supersymmetric quantum mechanics on the moduli space of branes. That's fine. But we would somehow like to understand how to go away from zero temperature. We'd like to describe things like boundary gravitons and so on. So this is largely a review of what I just said in words, but I'll just say again that Hawkins calculation simply fails at low temperatures. And as I said, we have to replace it by quantum statistical mechanics of what stuff? I put this as a question for the audience. I don't actually want to have people answering during the talk, but this is a question to think about, is that do microstate geometries give a concrete answer for what the quantum mechanics in the throat region is, and how do you resolve this basic problem with the Hawking radiation failing? So this is not supposed to be a question about the dynamical black hole evaporation process. This is a question about, does the assumption of thermal equilibrium even apply at low enough temperatures without quantizing the geometry, but quantizing the geometry in some sense that is left vague here. And as I said already, it's difficult to incorporate excitations, reaction, boundary gravitons. So pure ADS2 holography seems naively somewhat different than other examples. So the key fix that I'm going to describe is this proposal by Kataev and elaborated by many authors, which I'll give in a few slides, which is that we should move away from the exact ADS2 geometry, take the low temperature deformation around ADS2 seriously, and then imagine, of course, that ADS2 is really embedded in a bigger gravitational theory, so that we consider a very long throat that becomes almost ADS2 or nearly ADS2, but we still include the effects of finite temperature. And so in this previous slide here, the idea will be that in Euclidean, we'll cap this off with the Euclidean horizon, but at low temperatures, we'll develop a very long throat. And the idea will be that at some point, we'll sort of slice the geometry off somewhere in the throat region, put boundary conditions there, and then we'll treat everything above that point as just being classical. So you evaluate the classical action, that will supply the extremal entropy, that will supply the extremal energy. So all the extremal things, and it will supply the coupling constant for the effective theory that lives down here. So far away, where gravitational effects are weak and we can use the semi-classical approximation, you use that. Down in the throat, you actually try to do the gravitational path integral down here. And now you understand that there's some boundary conditions that you place. We've chopped this far region from the near region. And we're allowed to do that because we're letting the far region, we're letting the ADS2 region become longer and longer and longer, but we're still keeping the temperature finite. So there is some point where it goes back to being an asymptotic ADS or flat space of higher dimension. So the picture here is that we have a disk of ADS2. This is taken from the Moldasena Stanford Yang paper very shamelessly. So you imagine some disk of ADS2. This might be empty ADS2. And then we could imagine different geometries. So as I said, we're going to do some kind of Euclidean path integral. And we're going to sum over different geometries that have the same total boundary length, because the boundary length is the temperature. So we're computing a partition function at a fixed temperature. So we'll compute the partition function at a fixed temperature, which means fixing the length. But we can allow different geometries which have the same total length but differ by reparameterizations of the boundary. So this reparameterization mode is essentially the analog of the boundary gravitons that you would see in the ADS3 cases of holography. So this is this ADS2 manifestation of that. And it turns out that the path integral for this kind of theory is simple enough that it can be solved exactly. One more point that I want to make very clear. I am talking in this talk entirely about higher dimensional black holes. Isn't there a clock here, by the way? Is that accurate? Oh, how do I see the time? Okay, all right. I'll move a little faster. Yeah, like 15 minutes before. Yeah. Okay, thank you very much. So I'm going to be focusing on higher dimensional black holes where we tune the temperature low. And then there's various ways of seeing how this appears. There's this cutting and gluing construction of the near region and the far region. There's the idea that I could dimensionally reduce my higher dimensional black hole to an ADS2 effective theory, and then expand the ADS2 effective theory in the low temperature limit. That would give me JT gravity, or one of its supersymmetric extensions, which is a dilaton gravity that's almost trivial except for this boundary mode. Or what I could do with the approach in this talk will be that we'll avoid talking about all the dimensional reductions and cutting and gluing, and we'll focus on the idea that the higher dimensional black hole partition function can already be expanded at temperatures. We can identify all the saddles that contribute to the gravitational partition function, and then we will compute the one loop determinant around those saddles using the Schwarzean result. So the Schwarzean being essentially the extrinsic curvature evaluated on these different cutout geometries. So let me explain what that is now. So one way of getting the Schwarzean is to and motivate ADS CFT holography. This story has probably been said many times already, so I'll go through it quickly. But we want to build some kind of ADS2 holographic dictionary. We can talk about the SYK model as sort of a prototype for the kind of thing we want to see happen. So I'll build the dictionary between field theory and gravity, that we have a large N quantum mechanical system, that it's one-dimensional quantum mechanics. In the infrared, it develops a reparameterization symmetry, which is like saying ADS2 has diffeomorphisms that act. I say plus higher spin potentially. Now, these reparameterizations are spontaneously broken to the conformal group because correlation functions will be conformal invariant in general, but not reparameterization invariant, which is like saying that the choice of an ADS vacuum of my gravitational symmetry has an SL2R symmetry. So I break the diffs by picking an ADS2 solution. However, as I said, we want to go to finite temperature. So we actually turning on finite temperature explicitly breaks the SL2R. And in the gravity side, the finite temperature deforms this ADS2 boundary, giving me nearly ADS2. So then when I ask, what is the mode that captures the energy, captures the breaking of this SL2R? In the field theory side, one could find in solving SYK, for instance, one could find the Schwarzean theory. And in the gravity side, the extrinsic curvature evaluated on this wiggly boundary gives me this Schwarzean EFT. So the theory that I'm going to quantize is actually the extrinsic curvature of the ADS2 that's being glued to the higher dimensional black hole. That is the specific theory that we're going to quantize, except we're going to do a supersymmetric Schwarzean, which comes from higher dimensional black holes. So SYK itself is hard to directly build into a UV setup, maybe impossible. It involves, to solve the model, it usually involves random averaging over random couplings, which seems very unquantum mechanical. You may not like this model, though it does have some very interesting features in relating to quantum chaos. But even without thinking about SYK specifically, this Schwarzean mode appears to be something universal that shows up anytime you have a conformal symmetry that's a reparameterization symmetry that's spontaneously broken, and then a finite temperature that explicitly breaks it. The Schwarzean is really capturing the breaking of this conformal symmetry. So this is sort of an EFT argument that whenever you break something like SL2R or a supersymmetric extension, you'll get the Schwarzean EFT at low temperatures. And this can be verified in lots of examples, which have been checked for non-supersymmetric examples. And the supersymmetric ones we've cataloged as well. You can see this. So let me give you the catalog. So first, the Schwarzean derivative is this crazy nonlinear looking derivative with third derivatives and quadratic squared. This is a very unusual thing to have appear. And it's kind of surprising that if you just cut the ADS2 boundary out, it's along some curve, and evaluate the extrinsic curvature on that curve with fixed total length, the Gibbons-Hawking-York term becomes this Schwarzean derivative. So it's motivated from gravity, and that's in the Moldesana cited that here. And what I'm saying is that the action then, the Gibbons-Hawking-York action reduces the integral of the Schwarzean. Now, if we include dimensional black holes that might have ADS2 cross S2, for instance, or ADS2 cross S3 cross S5, things like that, then we might, in addition to the Schwarzean mode, have some, say, particle moving on a group manifold, where the group manifold will be the isometries of the sphere we reduced on. And of course, also for the supersymmetric versions, there'll be plus fermion at completion, which actually make the action very complicated. So it turns out when I write just the boson parts, it's very simple, but with the fermion interactions, it becomes very complicated. So if we, depending on the amount of supersymmetries that we have, we might have the broken symmetry group being SL2R, that's the standard case. OSP, if we have turn on a little bit of supersymmetry, SU111/1, which will be the case I'll study most in the second half of the talk. and n equals 4 Schwarzean, which has this broken symmetry PSU 112. And they all have higher dimensional black holes where you can explicitly do the dimensional reduction, find this two-dimensional dilaton gravity in the throat, look at the boundary conditions on the Schwarzean, quantize it, and you will find that these theories may or may, you can get the density of states basically from the Schwarzean path integral, and you may or may not have a gap in extremal degeneracy. And what I'm going to say is that in the cases of extended supersymmetry, you do get something that looks like microstates. So this is the case that I'm going to study. Oh, I could say that the coupling of the Schwarzean theory is exactly this gap scale I mentioned at the beginning, which is where Hawking's calculation broke down. It's the energy scale where the Hawking calculation broke down. Yes.
Okay. Can you make any coupling between the Schwarzean and the motion on the group manifold?
Oh, yeah. Sorry. They're coupled through in the supersymmetric. So in the supersymmetric case, there are couplings between all of these fields. In the non-supersymmetric case, you sort of, it's the partition function will be the Schwarzean partition function times a G manifold partition function. Yeah. So and in general, you can make more complicated examples where there will be couplings between them. Yeah, absolutely. And the couplings are very important. I'll show you the results for SUSY and non-SUSY, and they're well, they're similar, but they're also completely different, if that makes sense.
Wait, not
yeah.
done yet.
Okay,
I'm confused about the second line.
yes.
Where I think people in the room think they know a little bit about BTC black holes and their dual to symmetric product conformal field theories, which
Yes.
definitely have a gap.
So what I'm saying here is that if I take a two-dimensional conformal field theory with 1,1 supersymmetry, or there are other examples as well with higher supersymmetries, but and I demand, for instance, that so it's going to be the partition function in the supergravity regime and not in the symmetric product orbifold regime. And what I'll say is that I can use the trick, at least for 2 dimensions, that I can do a modular transformation. And if I make some mild assumptions about large central charge, twist gap, and do a modular transformation, the partition function and the boundary field theory can be given by kind of a Carty-like formula with supersymmetric extension, extended Carty, some people call it. So that's saying that's far from the symmetric orbifold point. That's at the point where you can essentially make the claim that the gravity dual is some Chern-Simons gravity theory. And that's the case where you can get these Schwarzean theories in the bulk. So I'm making a claim about in the supergravity point.
Right, but
which is far on the conformal manifold from the
it's
symmetric
far,
orbifold.
but in trying to imagine where even if it's far, there's some general intuition, maybe it's wrong, that the entropy comes from this sort of long string phenomenon, even when the thing is strongly interacting.
Even when the thing is strongly interacting.
And that suggests that there's a minimum gap, which is basically the length of the 1 over the length of the long string.
Yeah, this is a fair intuition. I suppose the claim for me is that we don't really know exactly what's happening when you don't have enough supersymmetry and strong coupling. We don't really know, and sometimes your semi-classical intuition might be valid. Actually, I've been thinking about this case. That was another one of the, we'll come to that question, is that in these ADS3 cases where we think that, say, I think in one of the other talks today, we sort of thought that the spectrum was protected, even though there was no supersymmetry protecting it. That statement was made. That sort of contradicts what we've done with what we see from the ADS2 throat, right? We use just pure gravity. We're not talking about string theory, just supergravity, quantizing the near horizon geometry. This is the result that you get. I don't know why how that squares with this long string picture. I honestly don't, and one of the reasons why I'm here is because I wanted to get input from people on that. I would say, though, that without supersymmetry protecting you, generically, quantum gravity effects near the throat will destroy nice features that we may have expected. It's a question I'd like to discuss it after the talk, actually, because I think that's one case where I'm not totally sure what the resolution would be. But generically, without supersymmetry, you will expect strong quantum corrections. So, and that's we find here what I would call the generic situation without modification from string theory. Yet, I'll get to that later. Okay, let me get my phone out here so I can. Yeah. Okay. So let me describe now the result that we get from computing the partition function of this theory, which is again computing the extrinsic curvature on a family of nearly ADS2 geometries. So the funny thing about this partition function is, even though it's a crazy nonlinear theory that looks almost impossible, the path integral for this theory and its supersymmetric generalizations is sort of an integral over a symplectic manifold with a U1 action. And it turns out that these partition functions are one loop exact because they localize using a version of the Dustamont-Heck theorem. So this is not a supersymmetric localization, but it is a fermionic localization in the sense of a path integral over a symplectic manifold. So the reason why we can make like fairly strong statements about what the partition function looks like in the throat is because when you reduce down to this effective theory of the near horizon region, you get a path integral that you can evaluate by saddle point, and it's a one loop exact. So that's where these results ultimately come from. I won't go through the calculation in detail, but you can see in our papers or in the Stanford Witten paper that did this in a variety of examples as well. So what is the result for computing the partition function and then the density of states of this theory? So the result that we get, and this slide title is meant to be very provocative for people here, so I hope there's lots of discussion afterwards. So this again addresses the point that you were just asking, is at low enough temperatures, do there actually exist, in the quantum theory, are there actually extremal black hole microstates? So this dotted line in both of these graphs would be the Hawking style result, and the pink curve is what you would get for the density of states from the Schwarzean theory. So in Einstein gravity, and this would be say for a Ricer-Nordstrom black hole. So an ADS2 cross S2 geometry, similar to what was discussed just before. If you have Einstein gravity, and this phi r is the mass gap scale I was talking about. In Einstein gravity, you get this cinch curve that's a smooth density of states that goes to 0 at 0 energy. So if you're like me, and you may have seen people talking about this Schwarzean theory, and you saw this cinch density of states a while back, you might have thought that this is nonsense because it badly disagrees with the Hawking result. It doesn't seem to reproduce the Strominger-Vafa entropy counting. It seems to be a very funny curve. Oh, it's also continuous, so it's not doesn't correspond to any quantum mechanical theory. What I'm saying is this is sort of an effective density of states that, perhaps if we had non-perturbative corrections, or if we could really resolve individual microstates, this curve would be some very tightly spaced delta functions. So the Schwarzean, what I'm telling you is that the Schwarzean only can give you smooth curves in some sense for non-supersymmetric Einstein gravity. And unfortunately, in this case, I mean, it has a lot of properties we don't think are realistic. But if you take the calculation of the Schwarzean seriously, it means that for non-supersymmetric black holes, their degeneracy really goes to 0 at 0 energy. The situation is significantly better in supergravity, and I think this is one of our first real major results, is that in supergravity, we actually find that the density of states still has a cinch-like curve that goes to 0, except that it goes to 0 now at some finite gap scale, which was exactly the scale where the Hawking calculation broke down before. And then separated by a gap scale, then again, we have some extremal degeneracy, which gets back exactly e to the S0. So for some reason, the supersymmetry conspires to leave a gap in this region and a delta function of states. That's rather surprising. It's very non-trivial that this happens in supersymmetric examples. We can also compute the index in this theory, and we also get e to the S0. So we could compute the index from the supersymmetric index from the Schwarzean theory and reproduce this as well. This gap scale was also argued to exist by a paper by, I think, Maldacena, Susskind, and Maldacena Strominger argued using the free long string description that there should be a gap scale. And they got from the free string theory picture, they got this 1/8 phi r. Well, in the D1, D5, this is like 1/8 q cubed or something like that. So it's very surprising that the Schwarzean theory, which seems to know nothing about string theory, and we only input the right amount of supersymmetry and did the quantization, you get this gap scale that came from a string theory argument, and you get this extremal degeneracy, which could be counted by the index.
So when you say supersymmetric theory, what extra degrees of freedom do you actually add in order to get that?
So let's say let's say this is the result for an ADS2 cross S2 black hole that comes from taking, let's say, type 2b string theory on a Calabi-Yau threefold, take the graviphoton multiplet, and then put an ADS2 a black hole that has a nearly ADS2 cross S2 region there. So I think one of these STU black holes or the D0, D4 would fall into that class. But the point is that you get one of those n equals 2 Reister-Nordstrom black holes. And then, so in the throat region, you have, in addition to the metric and the dilaton that come from JT gravity, you'll also get a Lagrange multiplier. Well, in the case for the S2 horizon, that has an SU2 isometry group that acts. So you'll get an SU2 value gauge field along with an SU2 Lagrange multiplier. And then you'll get gravitinos, so a pair of complex gravitinos with the fermionic Lagrange multiplier. So then in this picture, you have the Schwarzean, you have a particle moving on an SU2 group manifold, and then you have the fermions, which are basically the boundary components of the gravitinos. So it's like the supersymmetric completion of the extrinsic curvature. That's what you would get. And then that's a very complicated localization integral. And in the end, you'll get exactly this result, which reproduces these arguments that came from string theory from a seemingly unrelated looking calculation. So
is the answer to my question that actually you don't have minimal super BTZ, that you have an R symmetry?
That is the partial answer to your question, is that with n equals 2, so in 2, 2 supergravity, you get exactly this. I mean, the curve is a little different because there's different bumps from the different super multiplets. But with n equals 1, the claim is that the quantum corrections are strong. It destroys the geometry, and that's why I'm saying So by non-supersymmetric, I mean non-supersymmetric enough. You need to have enough supersymmetry, and then I'll say that there are extremal microstates and there is a gap.
So I got the JT part, the SU2 part. What was the Lagrange multiplier you said?
So there's a Lagrange multiplier that essentially fixes the SU2 gauge field to be a flat connection. So it's some sense the JT gravity is like phi R plus 2. So the phi dilaton imposes the R plus 2. R is equal to -2. There's also a sort of BF theory for the F being an SU2 value gauge field. And then there's fermionic versions of that. So you can write down these super curvatures and you can write the whole thing as a PSU 112 BF theory, which makes sense because I said that in the ADS3 case, it came from a dimensionally reducing the Chern-Simons gravity, and that leads to
So this would be a dimensional reduction of a Chern-Simons gauge term.
In the ADS3 case, but what I'm telling you is that we also can do the ADS5 case, which I will hope to get to, although we're...
No, take time,
Okay. I mean, right now I haven't really written a lot of equations, but I'm getting a lot of questions. The equations are coming if we'll get there. So my claim is that we can do this from the 3D point of view. We can do this for a 4D flat space black hole, ADS3 black holes. Okay, let me say, so I said all this in words, but this is sort of a remarkable prediction of quantum gravity. Again, this Euclidean path integral with putting in any UV ingredients, just assuming that there's a horizon, assuming that we can do the path integral in the ADS2 region and evaluate the extrinsic supercurvature, do the path integral. If you are allowed to do the path integral on this disk topology, and integrate over the different boundary fluctuations of the different fields, you'll get this result, which includes this single set of BPS states. So the status of this continuum, it's clearly some kind of approximation of whatever the actual microstates are. I'm giving everyone in this room that these are non-BPS unprotected states. We can't resolve individual microstates. It's some kind of continuum. We ultimately want a theory that resolves this. But somehow the general shape of this curve is a very generic prediction of supersymmetric black holes. And the sense in which we get microstates is the sense in which the supersymmetric ones survive even all of this stuff that you wouldn't, well, of course they're supersymmetric, so maybe you would argue that they have to exist independent of the coupling, but the fact is that we really get them from a gravitational path integral. So the only microstates I get in this entire talk are these ones that sit right here, but I consider that to be a reasonable start. And of course, it reproduces the arguments from string theory. Arguments about this, or sorry, questions about this, arguments, questions? Any? Okay. So let me just give you a quick list of the examples we checked. I'm sorry about the slides here. For some reason, there was an error in the PowerPoint. But so we checked the d equals 4, n equals 2 Reister-Nordstrom, and that led to this n equals 4 JT gravity and the n equals 4 super Schwarzean. The n equals 4, 4 BTZ. So this is the BTZ inside of ADS3 cross S3. This gives you a similar Schwarzean theory. This talk, the second half of this talk, or last quarter of this talk, will be about the ADS5 black holes. And actually, the precise spectrum here does depend on the bulk theory. And then there is less supersymmetric examples as well. So I think all of this I just said in the course of answering questions. All examples possess a gap and extremal degeneracy if they have enough supersymmetry. We can also compute the index and match it with field theory when possible. And then quantum features, as I said, dramatically modify your semi-classical expectations. So non-supersymmetric microstate constructions should address these quantum effects on the spectrum, on the correlation functions. This Lin, Maldacena, Rosenberg-Shan paper has not appeared yet, but they discuss correlation functions in these supersymmetric JT theories. Hi, yes. Oh, wait, yeah.
Thank you. So in your previous slide for the supersymmetric black hole.
Yeah.
Yeah, no, with the plots, with the two plots.
Oh, sorry. This
yeah.
one.
Yeah, this one on the right.
Yeah.
So usually, in chaotic systems, such as we expect the black holes to be, you don't have any degeneracy in the spectrum.
Yeah.
While here you have a delta function with some e to the s degeneracy.
That's right. That's right.
So is that, but does that mean that since these are like supersymmetric, they're somewhere in between chaotic?
Exactly. That's
and
the
not...
subject that this paper one is writing right now, is that these supersymmetric states that we found, it's an integrable subsector of some kind of chaotic system. That's precisely right. Yeah, the supersymmetric states are these special, seemingly integrable states, and that other things, yeah, they'll be densely packed, almost randomly distributed microstates, and then there's a protected subsector that we can count in various means. Yeah, I think that's the picture that's emerging. I mean, the paper that I'm referencing has not appeared yet, so we'll see what they actually say. But I think that's
makes
the idea.
sense.
Yeah. Okay, so our main example today, we'll see how far we get through this, is the quantum corrections to black holes inside of ADS5 cross S5, in particular the Gutkowski-Rialp black holes and the Chang, Shvedich, Pope, Liu black holes. And so our plan will be to consider a black hole in asymptotically ADS5 cross S5 space in the grand canonical ensemble. And then these black holes are supposed to be dual to heavy operators in n=4 super-Yang mills, labeled by some quantum numbers. So for some values of the charges, particularly charges of scale of like n squared, and with some obeying some constraint, the black hole is BPS, extremal, and supersymmetric. And the BPS states have an exact counting in string theory. And there are these 1/16 BPS states in the dual theory. So this is fairly well understood in field theory in the sense that we sort of know what the BPS states are. Actually, counting the BPS states in n=4 super-Yang mills was sort of a long-standing open problem that was only recently resolved by a number of authors who will get to their work in due time. And that was compared with the supergravity answer. So the index in field theory has been matched to the supersymmetric black holes. But as I said, I want to go away from the exact extremal BPS answer and look at the near BPS states by turning on finite temperature. So we're going to turn on finite temperature and chemical potentials. And then we're going to essentially find the ensemble that we want to use to do the computation that will reduce to the Schwarzean when we evaluate the partition function. And in order to determine exactly the setup of the problem, we want to use the bulk geometry, find the broken symmetry, and find the super Schwarzean mode. So we'll determine what's relevant, quantize it, and then we'll ultimately give a prediction for the near BPS states of n=4 super-Yang mills using this low energy effective gravity description. So in view of time, I'm going to go a little bit quick through the technical details, which I'm sure many people will want to see that there were technical details, but maybe not want to see. You said don't wash your socks or something. So I'll go relatively quickly. So yeah. So essentially the setup of the geometry will be something that's near ADS2 cross S2, cross S3, sort of rotation on the S3. So this is an ADS5, asymptotically ADS5 geometry, cross an S5. And when I say cross, I really mean a fibration. So there's sort of a nested fibration of an ADS2 over an S3 over an S5. For practical reasons, we'll take equal angular momenta on the S5. So this is a black hole in 10 dimensions, and we're going to take equal rotations on the S5 just so that the solution in 5 dimensions is tractable. So I'm emphasizing that this is really not a 2D gravity calculation because one actually has to sum over different bundles of the full 10D geometry. So it's a little hard to see exactly what's going on if you only lived in 2D, but in 10D, it's kind of completely clear what manifolds and what solutions you have to sum over. So we'll fix boundary conditions at infinity and fix boundary conditions for fields on the thermal circle. So we'll fix some charges, some potentials. We will not include KK modes, which I'm sure is a very big question people have, is why are you only allowed to use like two-dimensional supergravity fields and not the higher modes? Please ask me afterwards because I'm already very, very, very behind time. I will be happy to explain why the KK modes are not relevant for this discussion, although we definitely would like to compute them. This includes the log type area corrections computed by Sen, in principle at least. We will include higher topologies, D-branes, orbital folds, all kinds of other stuff. We would like to include this stuff. This is step one of many steps to get further and further refined calculation of what the partition function is. So that is the setup. So to actually find the black hole solutions, we'll start with the 10-dimensional gauge supergravity. We'll only turn on the metric and phi form because those are the only ones that will be relevant for the 1/16 BPS black holes. We will start with a 10-dimensional metric with a Kaluza-Klein ansatz with equal rotations on the 5 sphere. So this is the metric ansatz. Here's the self-dual phi form. And this choice will set the ADS 5 radius equal to 1. This will lead us to, with these choices, we'll get what's called 5-dimensional minimal gauge supergravity. We've not turned on any hypermultiplets. It's a single vector multiplet coupled to Einstein gravity with a cosmological constant. There's also a Chern-Simons term, which is actually subtly important for getting the correct action. And everywhere in many formulas, there'll be a G5. You should just think of that as 1/n squared. So the point is that this action is proportional to n squared, and it's large in the large n limit. And in particular, the black hole saddles of this action are sort of the largest action solutions that you can find in this problem. So they'll dominate the path integral at low temperatures in a charge sector.
There are no, you've got no scalars. You've just got
no scalars.
So
no
it's around. It's around.
Yeah,
no,
and
no,
this is exactly the gravity theory that Krukowski-Real use as their setup.
Okay, but so there are no scalars on the shapes of the sphere.
Yeah. We can take a more sophisticated ansatz and get to a harder gravity. That'll be in a follow-up paper, I think. Yeah. Okay, so here's the black hole solution. I'm sure everyone's very familiar with this metric, so we won't dwell on it very long. It's a relatively simple form. You're supposed to just look at it and enjoy it and appreciate it. So it's essentially a ADS Kerr-Newman. There's 4 parameters, M, Q, A, and B. So the mass, the charge, and 2 rotation parameters. And it's dual to states that have dimensions, R, charge, and spin. Sorry again for the slides. We'll use Euclidean time, and then various fields will have boundary conditions that are determined by making this Euclidean black hole smooth at the horizon. So the point is that once you Euclideanize this metric, it looks like this capped off cigar. And we have to make sure that various fields are not singular at the Euclidean horizon.
One quick question.
Yes.
I thought that the Grotowski-Real black hole had a strange horizon shape. It's some kind of, or is that the Lorentzian form and I'm misremembering?
I don't think it has a weird, this is a well,
it's one
this has 2 rotations inside of ADS 5, and it's a, this is basically charged Kerr-Newman.
Okay.
Yeah, this is the specific metric that I wrote down came from Chang, Fedich, Liu, and Pope, which is just a slightly just a version of Krukowski. Yeah, but this is not extremal yet. This is not extremal yet. No, we'll do the extremal one in probably an hour or so. This is not extremal yet, but we will eventually get the extremal one. Yeah. So this has just generic parameters so far. This is not even BPS yet. So this has finite temperature and finite charges. So the charges and potentials, we can determine the potentials by smoothness at the largest value of this R plus. So there's some complicated expressions for the grand potentials, temperature, chemical potential, and 2 angular velocities. And the charges are determined by the ADM procedure. So they all go of order n squared, and there's some complicated, once again, complicated functions of the various parameters in the metric. So the grand canonical ensemble, the idea, remember, way back at the beginning, I said that I wanted to calculate Z in some ensemble. And the way I'm going to do that is by saddle point. I'll find the largest saddle point solution of the answer and just say Z is approximately that. Of course, there may be other saddles. There may be thermal ADS, there may be different flux sectors, non-perturbative corrections, et cetera, and so on. I'm just going to try to keep the largest one that I can see in supergravity. When we evaluate the on-shell action, you can find the Bekenstein-Hawking formula, you can get an expression for the action. And this thing, when you plug in all those charges and potentials, you end up getting this quantum statistical relation that the on-shell action in supergravity evaluates to this particular combination of potentials. This is just the statement that black hole thermodynamics works. And we'll use this grand canonical action. I can discuss various limits of the black hole. There's 2 distinct limits. So when the charge is not equal to this, basically when mass is not equal to charge, that'll be some, and the temperature is finite, that'll just be some generic ADS black hole. That was the metric I just gave you. If I tune the temperature to 0, but don't make it supersymmetric, I'll just get an extremal ADS 5 black hole. if I make it both supersymmetric and zero temperature, I'll get a BPS black hole, and stars will denote all BPS quantities everywhere. So whenever you see a star, that's evaluate the quantity at the BPS value. And the BPS quantities obey this very funny nonlinear constraint, which comes from simultaneously imposing t equals 0 and q equals m times angular momenta. This nonlinear constraint is very surprising from field theory. It's forced on you from gravity because it's a gravitational statement naively, because we use the Hawking temperature, this quantity is a gravitational concept. This thing makes sense in field theory, but this is more of something special to black holes, at least. Temperature is not special to black holes, but setting the temperature to 0 here gives you this constraint. And then finally, you might have, and again, sorry for the slides, you might have what I'm going to call a non-black hole. And that's something where I have finite temperature, but I've set this SUSY relation to 0. And this might sound like a paradox because SUSY states are supposed to have the lightest mass for a given charge, and this finite temperature, but SUSY sounds paradoxical. The point is that in Euclidean, you are allowed to do this. But if you go to Lorentzian, this will have closed time-like curves. So maybe we throw it on gravity. And I would click further to the slide, but actually you might ask a further question, which is that, wait a second, in field theory, I thought I'm happy to have some supersymmetric states that don't satisfy, I mean, they have M, I could make them satisfy the SUSY relation, but I could make them not satisfy this cubic relation. So that means that there are heavy states in n equals 4 super Yang Mills, which are not dual to black holes with a smooth Lorentzian interpretation. There are missing black holes. I will not consider them later in this talk, but it's a very interesting open question to understand what they do. So these 1/16 BPS states, they're dual to, well, the 1/16 BPS black holes are dual to BPS states in n equals 4 on S1 cross S3. We can break the PSU 224 global symmetry down to its Cartan, and we can write what I would call the grand canonical partition function, now thought of as the n equals 4 one, and that will be a trace over the Hilbert space in the grand canonical ensemble. Now, for fun, and also in a series of works that were very impressive, we could, if we like, take a linear combination of chemical potentials, set them to an imaginary value that is equal to -1 to the f, and then we could rearrange charges so we have something like e to the minus beta q cubed bar. And so this thing, a specialization of the grand canonical partition function, is the supersymmetric or is the superconformal index. And it was shown in many papers that I couldn't include here, but in the works of all of these authors over the last few years, early works here and then more recently, it was shown through different methods that when you compute very carefully the superconformal index of the field theory, you always get this I sugra, where I sugra was that grand canonical ensemble action that I showed you, built out of just things that I computed from the black hole. You evaluate it for the BPS black holes, and they got that the index on the field theory side was equal on the index of sugra. That was what I was going to talk about in the discussion section next week. I won't say too much about the index here, but that's very interesting that this Euclidean gravity calculation reproduces some field theory calculation that they work in completely different ways. So I will say, however, that the index is really not in general equal to the degeneracy. I mean, the index lower bounds the degeneracy, but you could have cancellations between bosons and fermions. And the index automatically is temperature independent, so you can't see all these finite temperature effects I was talking about. So in some sense, the index counts that delta function of states that we're all very excited about, but it doesn't see any of this continuum, which we think a real black hole should have that non-BPS continuum above it. So let's talk about this next week. So I'll say now what we want to compute. So we want to compute Z. Now, when we write trace with e to all these chemical potentials, this trace is actually invariant if we shift the chemical potentials by some imaginary integer multiples as long as they satisfy some linear constraint. That's just an accident of writing trace potentials. So we want this, whatever we compute, we want this to be shift invariant. Shifts by these, beta omega-1 plus I n1 over beta, these kinds of shifts here. But the problem is that when we want to do a saddle point approximation, we take Z and write it as Z of saddles, e to the action times 1 loop. But when you write this sum of saddles, we lose that invariance under shifts. And let's say for a moment, and was explained in this paper, that we actually need to maintain this invariance under these complex shifts in order to get a sensible answer. We will impose that this shift invariance at the level of this one loop partition function. So, at the level of the classical action times the one loop partition function. So in the bulk, these saddles where I took different chemical potentials and shifted them by integers, these are actually new black hole solutions in Euclidean signature, and they satisfy the same boundary conditions as the black hole I've been talking about for the last 10 minutes. They satisfy the same boundary conditions, but they're different black holes. And indeed, we'll have to add up a bunch of Euclidean geometries in order to reproduce things like the index. So this is an important technical point, but we have to sum over flux sectors, and that's also what we would do in n equals 4 super Yang mills. So we're going to sort of do the same calculation on the bulk and the boundary. Okay, I'm going to move a little bit quickly through this. So we can rearrange this partition function. We can define some new things, introduce some new charges, and we'll pass to some kind of mixed ensemble where the near BPS black holes that I'm talking about dominate the ensemble. So this is some technical stuff. I probably shouldn't have put this here, but in the end of doing these various manipulations, we can work in an ensemble in which we have a sum over a single set of flux sectors, a single set of shifts of these different potentials, with e to a mixed ensemble action times a one loop partition function. So this is just choosing some kind of grand canonical ensemble where we want to do the computation. In general, you could choose different ensembles, but it would be more difficult from the Schwarzean point of view. So from the Schwarzean makes it easiest to compute things in this ensemble. Okay, so I was supposed to say some discussion words here about how, for the most part, we haven't actually used the near extremal near BPS limit. All the stuff I was saying at the beginning, we've been saying sort of classical things about the black holes and classical things about grand canonical partition functions. Now I want to go to the near BPS limit. So in the near horizon geometry, we're going to take the low temperature limit. And first, I'll take the 0 temperature limit. I'll find the action there, and then I'll expand around low temperatures. So in the low temperature limit, we're going to find new symmetries. So before we had ADS2, which had the SL2R symmetry. And then we turn on finite temperature. That gave me a wiggly ADS2 boundary. That breaks SL2R. In this ADS5 cross S5 black hole, I'll have not SL2R, but it will turn out to be SU111. So let's see how that happens. We'll analyze the extremal symmetries. We'll compute the Schwarzean parameters, and then we'll use the quantization of the Schwarzean. So, okay, we perform some diffeomorphisms, we go to rotating coordinates, and then we take the 0 temperature limit. And in the end, we get, this is the extremal metric that looks like a fibration of ADS2 over S3 cross S5. So there's this ADS2 factor in some coordinates. The ADS radius can be written in terms of the rotations. I specified to equal rotation for this part of the slides for simplicity. Otherwise, the formulas are a lot harder. And the gauge field determines some particular value. So we have an ADS2 cross S3 cross S5 geometry. So let's analyze this, the supersymmetry, because I told you the answer really depends sensitively on the supersymmetry. And we'll use the 10D killing spinner equation for that. So this is the type 2B Gravitino killing spinner equation. We define some complex spinners. And when you turn the crank and solve for the killing spinners available in this background with this gauge field, you will get some set of killing spinners. And the second one is the original 1/6 BPS killing spinner, because these were 1/16 BPS black holes. But we also find a new conformal killing spinner, which tells me that the near horizon symmetry has enhanced, as I've said, to a conformal symmetry. So these are the generators of the near horizon symmetries. They will end up forming the SU111 algebra. So the idea is that the Schwarzean mode will be the Schwarzean mode of essentially local SU111 reparameterizations. In particular, the U1, it corresponds to a rotation on the two angles of the S5, on the two angles of the S3 and on the S5 at the same time. So this thing I call the Schwarzean U1, this particle in the group manifold that we added, that's a rotation, big complicated rotation in 10 dimensions. Okay, so we're going to expand the action at low temperatures, and we find a mixed ensemble action at low temperatures. That has the extremal entropy. S star is the entropy of the ADS2 region. E naught is the entropy of empty ADS5. And then,
can you pause 1 second?
Yes.
Where's the mixing of this extra U1 with the Schwarzean, or isn't it mixing?
So I haven't written down the gravitational action. What I've written down is a metric, and I've told you the symmetries of the metric. Now, if I had more time and put extra slides in, I could show you that there's some JT gravity that realizes all these symmetries. So you'll see that there's essentially, it's a BF theory in ADS2, where the F is the field strength for this U1, which is this Z here is the U1. So what I could do is I could write down an SU111 BF theory. And when I expand it out, it would be some supersymmetric JT gravity, which one could get by doing this dimensional reduction. We didn't do the full dimensional reduction in this ADS5 example, to be honest, but we did it in other examples, the ADS2 cross S2, and the full 10D reduction is more technically complicated. And this approach sort of gets the same answer by an Eft argument, and it's the same as other examples we've done. So
in particular, there's did you reduce it in the presence of some non-trivial diffeomorphism in the throat, or just said, okay, here are the symmetries, and this is the effective field theory that has those symmetries?
For the 10D black hole, we did the effective field theory approach. For the ADS2 cross S2 one, we did the full dimensional reduction in the sense that you could take the supergravity action to start with, plug in an ansatz for the metric that looks like it has an ADS2 factor, and then you can you'll get some 2D dilaton gravity. You expand that at low temperatures, add the Gibbons-Hawking-York term, and then compute, and you'll get ultimately the Schwarzean for once you have to choose boundary conditions for the fields, and then you evaluate the extrinsic curvature with those boundary conditions, and you'll get the Schwarzean derivative. So in the lower D examples, we did the full reduction completely. In this example, we use an Eft argument, which someone could tell us it's invalidated. I have no reason to believe that's true. It works like all the other examples, seemingly. So, okay, so essentially, we use the higher dimensional action to feed us the UV parameters, and then we use the IR action that can be quantized exactly. And so the UV parameters we get come from the black hole solution. Again, they're very complicated combinations of the parameters. So in the end, this partition function was a sum of these shifted integer saddles of the classical action times the one loop determinant. And it will turn out that this actually has the same form as the partition function of this n equals 2 Schwarzean theory. So, so the specific Schwarzean theory that you get is this 1 over m SU111, this parameter that we computed from the bulk of a Schwarzean plus the particle moving on the UN group manifold plus the fermion interactions. There's a couple of discrete parameters because the gauge group is U1. There's a couple of discrete parameters, and we actually fixed their value. So actually computed a more general object. I'd actually like to talk to people about if there are bulk solutions that realize different values of these parameters, because you could have a potentially a theta angle term and a different spectrum of charges. But okay, I'll skip this slide because it's more general than we needed. But in the end, we find that the Schwarzean partition function, when we feed in the parameters from the bulk, we get an answer for the one loop determinant. So this came from expanding, computing the fermion zero modes and the zero, sorry. This comes from the one loop determinant of the metric and the fermions in the gauge field around each of these shifted saddles. So the final result, this is the Schwarzean partition function, but essentially the data came from the 10D black hole. Okay, I'm getting pretty close to the end, so I want to get to the result. So there was no topological term I briefly touched upon. There might be other theories that have it. And there were some discrete parameters that we were able to compute from the bulk as well. And as I said, if we take this partition function and set this chemical potential alpha to some particular imaginary value, that's equivalent to inserting -1 to the F. And we reproduce the index, which is e to the S star. So this is what the ADS5 cross S5 and n equals 4 super Young-Mills super conformal index people, they computed and they got exactly this answer from n equals 4 as well. And what we found was that in gravity, there's additional prediction, which is that the index gives all bosonic or all fermionic states with this -1 to the R star, where R star was some parameter on a previous slide. So in particular, this tells you that there's no cancellations between bosons and fermions in the index. That's a gravitational argument for why there's no cancellations in the index. Okay. So we can now, so this partition function is the final result, but just for fun, we can inverse the Laplace transform it and look at sectors of fixed energy and charge. So let's, I will additionally, I'll skip this slide, but I will convert this Schwarzean / gravitational data into the n equals 4 super Young-Mills data. So everything was computed using gravity, but the plots I'll give for the scaling dimensions and charges will be written in n equals 4 super Young-Mills language, because we're ultimately supplying a prediction for the density of states of super Young-Mills from this. So, so this is the density of states in a sector where the R charge is equal to what we call the BPS R charge. And so it has some complicated expression, and it reproduces the plots that I showed at the beginning, which is why I showed you at the beginning, because I thought that people might be a little tired by the end. So this is sort of a phase diagram where the vertical, essentially the horizontal axis is R minus R star, and the vertical axis is this delta minus delta gap. So there's 3 colors of lines here. The blue line is the semi-classical Hawking result in the delta R plane, because remember, delta is like the mass of the black hole and R is like the R charge of the black hole. So the blue line is the semi-classical Hawking result. The red line is the region that's excluded by being below the unitarity bound, and the black line is the Schwarzean result. So to further explain, so each of these vertical lines here that you see is one of these plots here. So there's sort of no black holes in this region. There's a gap. And then the first extremal black hole starts somewhere here, for instance, or somewhere here, or somewhere here. And then you see this continuum. And in particular, there's no extremal degeneracy for any of these points here. They're discrete lines, by the way, because charge quantization is satisfied. The charges are, the R charge is integers, as an integer spectrum. So each of these vertical lines is one of these curves. And this black point here, which is almost quite at the intersection of all these lines, but is not quite, is this one here. So exactly when the R charge, we work in a fixed sector of R charge, is equal to this BPS R charge, then you will find the extremal density of states, which is this point right here, where delta equals delta BPS and R equals R BPS. So these states are right here. And then there's a very small gap where the gap scale is set by this combination of rotation parameters. So we computed the gap scale, and then there's a continuum above that. So this is the main results for the phase diagram of the density of states. And this is written in N=4 super Yang-Mills language. So in principle, if you're very powerful at superconformal field theory on S1 cross S3, you could check if this result is reproduced. And again, of course, if you were very good at superconformal field theory, you would say, hey, I'm never going to get this. That's a continuous density of states. But the point would be that you would expect to find a very chaotic, densely packed spectrum, and then a very small gap of order 1/n², and then these BPS states, which I can count using the index. That would be the idea. If one could do a very hard, strongly coupled low temperature quantum field theory calculation. Are there questions about this slide? This is like the main result. So if people want to understand more, otherwise I'll move to the end. Okay. All right. So we can make some plots of energy and entropy. In particular, the density of states that you compute here resolves this Hawking quanta issue, because it will always force the mass to be below the quadratic curve. So this issue I mentioned about the low temperature energy of the black hole goes below the low temperature energy of a single Hawking quanta. Schwarzean corrections completely fix that. So we sort of resolve this paradox from the early 90s, and indeed give a more detailed prediction for what the spectrum should look like, the mass spectrum and energy and so on. Oh yeah, you know what, let's, because everyone was asking about alpha prime corrections, I included a slide on that as well. We can also take the higher derivative corrections of type 2b supergravity into effect. So this is the r to the 4th plus c to the 4th plus 5-form correction. So there's like a sum of 16 terms here with a particular coefficient that was computed, I think, by Michael Green. So this coefficient here, when they computed 5-form and 4 graviton amplitude. Yeah, okay. Okay, Green-Schwarz as well. Thank you, yes. I think maybe this coefficient was computed by them, but the full supersymmetric completion, like the off-shell action, was I believe Michael Green, then Paulus, and then Mello and Santos. So just for fun, we redid the entire calculation in the presence of these higher curvature corrections, and they will actually turn out to shift the Schwarzean coupling by an alpha prime dependent amount. So this lambda is the TÜV parameter, and so we can find TÜV parameter corrections to the Schwarzean. Because you might have thought that this spectrum doesn't look like a gauge theory, but maybe as we include stringy corrections, higher and higher stringy corrections will slowly get down to something that looks more like the spectrum of a nearly free gauge theory. Of course, this series has many dots before you get to weak coupling. But the point is that in principle, one can include it, and one can actually do a supergravity calculation with the Schwarzean with the higher derivative effects. So that's nice. So just to conclude, so we studied quantum effects in the gravity path integral at low temperatures. And as I've tried to emphasize, the quantum corrections invalidate many semi-classical results you might have expected. And somehow, because of the relative simplicity of the ADS2 region, because it sort of is, as Dieter was emphasizing, the ADS2 is at very far distance. You can almost chop the ADS2 region off, do the quantization there, and then try to match it to the external geometry. And ADS2 is simple enough that you can do some kind of exact calculation, and it gives semi-universal predictions for what you would expect. And in the case of the 10D black holes, we could compute something very complicated, and we get an exact result with the index that was computed through field theory techniques, and we give a prediction for the density of states, the density of states being something that's not protected. So it's not clear how you would compute it in field theory, but we have a universal prediction for what that should be. And there's some other directions one could attempt. So extensions of theories with other amounts of supersymmetry, other ADS spaces in particular. I think ADS4 is one that may have differences with what we did here. You can include non-perturbative corrections, higher genus topologies, D-branes, and so on and so forth, and also try to understand what's happening in the field theory. I think overall, I would really like to understand what is the theory that resolves the individual microstates. Why is it that the Euclidean path integral seems to get so many things right and seems to make so many detailed predictions for what's happening, even though we use what is ultimately a relatively simple theory of gravity? These are questions I'd like to see understood in the future. And also, if there's other geometries that we've missed, that when you include other geometries, they give you a more detailed prediction for the density of states. I think that's very likely that this is just the beginning and that there's a whole tower of things one would need to include. So with that, I think I'll conclude and leave it up to questions or something like that.
There have been lots of questions during the talk, but I think there are some more.
Yeah.
Right. So in the 5D black hole calculation that you were mentioning, getting the entropy involves a Legendre transformation with a constraint imposed on the fugacities.
Sorry, getting which entropy? So,
the entropy of the 5D black holes that you were mentioning?
Yeah.
Like the CCOP1?
Yeah.
Right. It involves having like a relation between the fugacities. Essentially, the sum of the fugacities is equal to 2 pi I.
No, sorry, that's the supersymmetric index.
Yeah. Sorry, for the supersymmetric.
You're saying entropy. For me, the entropy is just some number that you plug
Yeah.
action. You get there's a part that it's in.
No, No, I meant getting the
supersymmetric
entropy
index,
from the supersymmetric. So now,
yes.
do you see this constraint like between the fugacities somehow in your like JT description?
No, in fact, the point is that once you pass the Euclidean signature, I won't say all bets are off, but many bets are off because you can tune the chemical potentials to be whatever you like, and if you try to interpret those chemical potentials in terms of the higher dimensional geometries, it's as if you have complex geometries or complex angular momenta, which sounds a little bit strange, and that's why people had missed this. If you're, but I think you're maybe asking about the slide of why do we get this lower right corner? Well, there was a lot of slides. All right, you're basically asking where do we see this constraint comes down? So this is the canonical conjugate of what you were just saying. That geometries that satisfy these charges contribute to the index, which the index in the grand canonical is where the chemical potential satisfies some constraint. Yeah. So from the field theory side, this is very mysterious, whether you work in canonical or grand canonical. From the black hole side, these are just the ones that are both zero temperature and supersymmetric. So you ask, can I write down a partition function where only zero temperature supersymmetric black holes contribute? That partition function would involve tuning the chemical potentials to be that value. So you get a -1 to the F and that sort of thing. So sort of by design, if you want -1 to the F, you have to choose them to be that value. But in general, you can choose the chemical potentials to be whatever you like. And there are strange Euclidean geometries that are not necessarily black holes that will contribute depending on what ensemble you choose. So from the 2D point of view, it's not clear. It's a choice that you make in the ensemble, and it is the index by definition. Yeah.
These geometries are complex, even in the Euclidean.
Yes, because when you whenever you have some A times dt or something, some gauge field in there that appears linearly in the metric with a dt factor, and then you send dt to I d tau, yes, you'll get in general complex geometries, and we're okay with that. That was what Hawking and Ross, I believe, did way back in the day, and it probably sounded strange when they were doing it now, but people have made their peace with it to some extent because it computes things like the index. Although, again, I think we'll have a whole discussion on that as well. What's the meaning of the complex geometries? Why do they compute the index? And you might believe that the honest Lorentzian geometries have nothing to do with these Euclidean ones. That would be interesting as well, that there's a better Euclidean Lorentzian version of this calculation that doesn't involve strange geometries. They seem forced on you from this point of view, at least to get consistent answers. Yeah.
It's okay. It's okay. No. So just one comment. So about the mass gap. So
Yeah.
if you look at the extremal black hole, where we know all the we know many of the microstates. If you compute the mass gap above the microstates, what you find that is at a zero temperature, you have a huge amount of solutions. All the supersymmetric fastballs we are constructing, and then if you look at the mass gap above them.
So what's are you referring to the ADS5 setup or an ADS3?
In ADS3, in the previous,
okay,
you had a question before about ADS3 and how to get. So if you look at this e to the s, so you have an e to the s curve with a huge amount of entropy.
Yeah.
And then there's a gap, and then you start having. So if you compute the mass gap about each and every microstate, so you have a supersymmetric solution, and you can compute the mass gap above it. You have another one, you can compute the mass gap above it. What you find is that the mass gap above each and every one of them goes like 2 over n1 n5, which is what you expect from the CFT.
2 over what?
2 over n1 n5 in the D105 system.
Is it 2 over 16 or 2
No.
or just 2?
2.
Because we get q over 8 or something in this, which is what Modesena and
But
Susskind.
so the point is, in the D105 system, there's a CFT gap, which you expect. You have a CFT of some long string, and that's exactly matching the CFT gap. So you see the CFT gap in the bulk, and you see that above all the supersymmetric ground states, there exists a gap, and then there's a gap spectrum. But the differences differ, but the gaps are a bit different. So, if you look at, if you take, 20 microstate geometries, which are all supersymmetric, you have at energy 0, you have 20 of them. And then at energy 1 over n1 n5, you start having, you have the first state, and then you have the tower, but then because the towers are different, you basically will end up getting some density. So you have a number of states which is actually increasing.
Sorry, are you saying that the gaps are slightly different, or that the gap is always the same?
No. So the point is they are slightly different from each other. So the first one is 2 over n1 n5, but then the next ones are a bit different. And then if you compute that, if you do that, if you just imagine taking a huge amount of zero energy solutions and computing all the mass gap, you'll actually find something filling up. It
closes all the way. But is there so this curve is drawn on the scale of e to the s naught. Is there an order 1 number of guys here, like very small numbers here? Or
the point is there's nothing. So the point is between the ground state and the first state, there's nothing. All the mass gaps are over the 1 over n1 n5, and they cannot be smaller. Because from a CFT perspective, you cannot have a smaller gap.
I see. So this plot, the specific example where this plot is from, the gap is of order 1 over n squared, but that was for the gauge theory example and not the D1 D5. So
yes.
So but are you saying then that you agree that
I think in all the ADS2 systems, you can actually construct asymptotically ADS2 microstates which have a cap at the bottom. And I think this is going to be a universal feature. All the ADS2 throats can be capped in the infrared. And then if you solve the wave equation above them, you'll actually find a tower of states. The difference between ADS2 a la Strominger-Maldacena is that Strominger-Maldacena have an infinite ADS2. If you cap it, if you build a supersymmetric cap, then you can build a nice tower, and the energy actually lives in the infrared, and then you can see the gap. You can see the gaps above, and I think that's what you're finding here. You're finding these gaps.
Okay. Let's talk more offline, because I wanted to ask about this very much in particular. So that sounds interesting. Thank you.
Oh, there's a question on Zoom. Yeah, just a question on Zoom from Samir Matur. What is the energy gap to the next state after the gap?
The energy gap to, so it's hard to have a dialogue with the Zoom question, but you're saying, so we had this gap here, which is, I should emphasize, it's a statistical prediction. I'm not saying that all microstates are forbidden there from this approach. They might be forbidden from a different approach, but but do you see a tower? The question is, what is the meaning of this continuum? If the question is what is the meaning of the continuum, then I would say that these states are exponentially close together. E to the minus s naught roughly is that's the expectation. It's invisible in what we're doing, because again, what we're doing is not the ultimate quantum theory of gravity that gives you all the densely individual pace. That's not what we're doing. So I believe that the answer would be the expectation is e to the minus s naught.
But you don't have any clustering at the first thing, and then some other clustering which opens up.
No, I can say a little bit more, which I skipped, which is that this curve is actually a sum of contributions of different supermultiplets. So you can count you can count as different multiplets of different different R charge begin entering the spectrum. So you can resolve this curve into a sum of cinches. So there's sort of a density of supermultiples picture that's happening here, but there's no clustering. The spacing between those supermultiple contributions is of order 1 on the scale. Yeah.
Can you show that next in the workshop?
Yes.
Oh, the sum. Yeah.
The gap is 1 over n squared.
Yeah, the gap is this quantity here over yeah. The gap is 1 over n squared. Yes, that's right. So in particular, it's polynomially small and not exponentially so. Whereas in the non-supersymmetric case, the gap becomes exponentially small, which I think it sort of makes intuitive sense that supersymmetry would. Yeah. Thank you for all your questions.